Okay, students, good morning. This is a class of geotechnical engineering. So we are discussing about module 2, that is permeability of soil. So up to last class, okay, so in the last class we discussed about how to determine permeability of soil for or in case of a stratified soil layer. Okay, so we also done some two numerical in the last class. So I advise you to go through your textbook or any reference book and try to solve similar kind of problem that may be given in the textbooks. Okay, so today we'll discuss about seepage of soil. Okay, so what is seepage? It is related to your permeability. Okay, so the basic difference between permeability and seepage of soil, that permeability define the property of soil, okay, by which allow the water to pass through its interconnecting voids within a soil mass. Okay, that permeability, it's a property. Okay, but when it comes to seepage, it is the phenomena of passage of water through soil. It means the occurrence of the flow of water through the soil. The whole condition, whole the scenario, the situation is called seepage of water through soil. But the property due to which water is flowing through the soil, this is known as permeability. Okay, so there is a very a small difference, difference between permeability and seepage. You have to take in mind in that. Okay, so what is during the water flowing through the soil mass? That means water flowing through the interconnecting voids. That water exerts some pressure on the soil particles. Okay, and you can say that the water passes through the soil under some pressure, and that particular pressure is known as seepage pressure. Okay, so what is different definition for seepage pressure? It is a pressure that can be exerted by the water on the soil particle through which it's flowing. Okay, or through which the water flowing. Okay, so this is seepage pressure. Okay, and related to seepage analysis. Okay, the seepage analysis mainly done in case of design of a dam. Okay, so related to dam, you all know in hydrology, you have already got the basic definition of dam. Dam is a what? Is a hydraulic or you can civil engineering structure constructed across a river. Okay, for multi-purpose operation or multi-purpose facility. Okay, so basically it retain the water in upstream phase. Okay, you can hold the water at in one phase of a retaining wall. Okay, or you can set a dam. Okay, so in design of dam, we need to study the seepage of water, because since in a one side water will be stored, and the height of the water so high, the water may exert some pressure on the upstream face of the retaining wall or upstream face of the dam, and water tries to seep, or water try to flow through the dam material, and this particular flow water under pressure through the dam material is known as seepage. Not exactly, not only through the dam material, through the soil actually. Okay, so if the water flow through the dam material, and if the water cross the opposite face of the dam, it may fail that dam structure. So we need to study the seepage, or you can say the flow pattern of water through the dam material. And for that, we need to understand the basic some basics parameter of flow water through soil. So it is known as seepage of water through soil. Okay, so it's a very introductory class. Okay, so fine. So in seepage analysis, one of the very famous equations is exists, basic equation. It is known as Laplace equation. I think in hydraulics also you will get to know this thing about had a Laplace equation of one-dimensional flow. Okay, so today we'll discuss about Laplace equation of flow through soil mass. Okay, okay. First, let me share my screen. Okay. Okay, is it visible? Please do respond.
Sir,
Okay, ठीक है. So it is just a class notes prepared by me a very long time ago. So about Laplace equation. Okay, let me zoom it. Okay, here you can see that title. It is a two-dimensional flow. Okay, it's my mistake. Sorry. So it's a two-dimensional flow equation proposed by or derived by Laplace. Okay, that's why the particular equation of Laplace is known as Laplace equation. Okay, so here you can see this rectangular shape of a particular thing. It is considered as a soil element. Okay, you can consider as a porous medium. Okay, of dimension delta x in x direction, delta y in y direction, and having unit thickness. Okay, unit thickness means in the perpendicular direction to the plane, the dimension is considered as a one unit. That's why you can say this is a two-dimensional flow. Okay, if it is a three-dimensional flow equation, then you can say there must be some thickness of the soil mass. Okay, but here thickness of the soil mass is considered as one. That's why it is known as two-dimensional flow equation. Okay, so in this diagram, you can see this is a porous medium, or you can say saturated soil mass. Okay, having dimension delta x in x direction, delta y in y direction, and water is allowed to pass in x and y direction both. Okay, here you can see water is flowing in this direction with a velocity of vx, and water flowing inside the soil element in perpendicular direction or y direction with a velocity of vy, and the the water coming out of the soil element in x direction y direction with this velocity, with a increased velocity. That means when water come out of the system or come out of the soil mass, since the area will increase at the exit point, that means the velocity will also goes on increase. That means within the soil mass, during this passes of soil passes of water through the soil, the velocity of flow at the exit will goes on increasing. But how much increase is this much? This much amount of velocity will increase in x direction. This much velocity will increase in y direction. So how to find out this? That initial velocity or velocity at the entry, that means Vx plus del Vx by del x multiplied by the length traveled by the water. Okay, and the length traveled by the water is in x direction is delta x, and in y direction the length traveled by the water is delta y. Okay, so that means the change in the velocity with respect to distance. The change in velocity, that is the change in velocity in x direction with respect to x direction multiply by the total length traveled by the water. So like this you can find out the increment in pressure or increment in velocity throughout this soil element. Similarly in y direction, del Vy by del y multiply delta y. Okay, so here this is all about the diagram. Okay, so this Laplace equation, mainly in this Laplace equation, the quantity of water flowing through a saturated soil mass as well as the distribution of water pressure can be estimated by the theory of flow of fluid through porous medium. And this is a theory. By this equation, by Laplace equation or two-dimensional flow of Laplace equation, you can find out. Okay, wait. You can find out the distribution of pressure distribution also, okay, so distribution of water pressure distribution, also the amount of water flowing through a particular soil mass can be determined by Laplace equation. Okay, so now very important term is now assumption. So during the derivation of equation, the Laplace have considered some assumption. Okay, so these particular assumptions are very important. 5 assumptions are there. So first assumption is what? So Laplace considered that the saturated porous medium is incompressible and the size of the pore space does not change with time regardless of the water pressure. Okay, incompressible means you cannot change its volume. Okay, you cannot change it in changes volume. That's why you can say the pore spaces will remain same throughout the experiment. We can say throughout the experiments when the water flowing through come inside and come out, throughout the whole condition or whole scenario, the pore space will remain constant. That means you cannot compress the soil mass. Okay, then number 2, Darcy's law is valid. That is, Darcy's law of flow through porous medium is valid. That means Laplace have considered Darcy's law and he accepted the Darcy's law of flow of water through soil. And you know what is Darcy's law? Q is equal to KIA or V is equal to KI. These two equations are valid in this particular derivation. That means he accepted that Darcy's law. Number 3, there is no change in the degree of saturation in a zone of the soil through which water seep. Seep means water flow, okay? And the quantity of water flowing into any element, okay, the quantity of water flowing through any element of volume is equal to the quantity of water flowing out in the same length of time. That means as per the assumption number 3, it is saying that the quantity of water entering the soil element must be equal to the quantity of water coming out of the soil element. Okay. Next, number 4, the hydraulic boundary condition at entry and exits are known. That means at the entry point and at the exit point, the boundary condition, hydraulic boundary conditions are water. They are like the value of Q, that is discharge, the value of velocity or velocity of flow or hydraulic gradient. All these boundary conditions are known at entry and exit point. That means you have to know these things. Okay. Then finally, water is incompressible. You cannot compress the water. It is the assumption. These 5 are the assumption of Laplace equation. Okay, in some exam may ask about that particular assumptions. Okay. Now let's go to the derivation of the Laplace equation. It's very simple. Okay. So already these things are already discussed. Consider an element of soil of size delta x, delta y. Okay, this is the dimension in x direction, dimension in y direction, and of unit thickness perpendicular to the plane of the paper. Since it is a two-dimensional flow equation, so thickness is considered as 1. So unit thickness perpendicular to the plane of the paper. Now let Vx and Vy be the entry velocity component in x and y direction. It is already given in the drawing. And this Vx plus del Vx by del x multiply delta x and Vy plus del Vy by del y multiply delta y will be the corresponding velocity component at the exit of the soil element. Okay, these things also already explained in that diagram. Okay, now as per assumption number 3, what it is the assumption number 3? That is as per assumption of Laplace equation, the quantity of water entering the soil element must be equal to the quantity of water leaving the soil element. So from that, if you can equate the quantity of water entering the soil element and quantity of water coming out of the soil element, you can get this equation. Now this equation derive what? Q. Okay, Q is equal to what? Velocity multiply the your cross-sectional area. Q is equal to VA. It is a standard formula for discharge, isn't it? So here you can see, if you consider for x direction, and the quantity of water entering in the x direction is what? Vx multiplied the cross-sectional area. Now what is the cross-sectional area? Delta y multiplied by the thickness of the soil element. Thickness is what? 1. And delta y is what? Perpendicular dimension. Perpendicular dimension to the x direction. Now delta y is in the perpendicular direction to Vx. That's why delta y into 1 is the cross-sectional area for water flowing in x direction. So multiplying Vx with delta y will get the amount of water flowing or amount of water entering the soil element in x direction. Similarly, Vy into delta x into 1. This is the amount of water entering the soil element in y direction. Okay, so same way, this term is the amount of water coming out of the soil element in x direction, and this is the amount of water coming out of the soil element in y direction. So after equating these two, okay, as per assumption number 3, equating water entering the soil element must be equal to water coming out of the soil element, you will get this thing, and after simplifying, you will get finally delta Vx by delta y, or delta Vx by delta x plus delta Vy by delta y is equal to 0. That means change in velocity or change in discharge velocity in x direction plus change in velocity in y direction must be equal to 0. Okay, and this particular equation generally known as continuity equation. Okay, this is known as continuity equation, and this is a very general equation. You also maybe you have already get this in hydraulics chapter or hydraulics subject. Okay, fine. So it is not a and some last something is still left. So this is your quantity equation. Okay, next go to the next. After getting the continuity equation, let's consider the assumption number 2 of the Laplace equation. Now as per assumption number 2, Darcy's law of flow is valid, that is V is equal to Ki is valid. Now considering this general equation, you can define velocity component in x direction Vx as Kx into Ix, and velocity component in y direction Vy is equal to Ky into Iy. Okay, so this is as per Darcy's law. Kx and Ky is what? Kx and Ky are the coefficient of probability in x and y direction. And I is what? I represent hydraulic gradient. Ix and Iy what? Ix and Iy are the hydraulic gradient in x direction and y direction respectively. And hydraulic gradient can be written as H by L. H means your pressure difference or head difference divided by L. L is what? The length traveled by the water. In x direction, the length traveled by water is represented by x or del x. Okay, and in y direction, it's represented by del y. Okay, so we can rewrite Ix equal to del x by del h by del x. Iy can be written as del h by del y. It's simply the hydraulic gradient in x and y direction respectively. Okay, after getting the value of Vx and Vy in this form, you can put this value in equation number 1 that already discussed in the last image. After putting the value of Vx and Vy in that continuity equation, you'll get this thing. In place of Vx, you will put this. In place of Vy, you put this. Okay, so in general, after getting this equation number 2, the multiplication of kx and h and multiplication of ky and h. So in generally, the multiplication of coefficient of probability and your total head difference or total head drop, the multiplication of coefficient of probability with the total head loss is known as velocity potential. Okay, here you can see phi is equal to kh. The multiplication of k with h, it is together they are known as velocity potential, and this velocity potential, it is defined by this symbol phi. Okay, we'll discuss about velocity potential in next class thoroughly, but For now, you just remember this. Then multiplication of k with h is known as velocity potential, and the symbol used for velocity potential is phi. And just put the value phi in the equation number 2. You will get k h in place of kh. You can put phi k into h, ky into h. You can also put in here phi. Okay, so delta square phi by del x square plus delta square phi by del y square. This particular equation is known as Laplace equation of flow in two-dimensional. Okay, so del square phi by del x square plus del square phi by del y square is equal to 0. That means double differentiation of velocity potential in x direction plus double derivation of velocity potential in both in y direction is equal to 0. Or you can say the summation of double derivation of velocity potential in x direction and y direction is 0. And this particular theory, or you can say this derivation, is done by this Laplace equation. This equation is proposed by Laplace. That's why this is known as Laplace equation. Okay, and if you consider isotropic soil. Now, what is isotropic soil? The isotropic soil is defined as that soil having same property, same elastic property in all three mutually perpendicular direction. Okay, isotropic material means what? Isotropic material means the particular material having same property or elastic property in all three mutually perpendicular direction. So if the soil is isotropic, we can say the coefficient of permeability in x direction and coefficient of permeability in y direction must be equal, since it is an isotropic soil, isn't it? So we can replace kx and ky from k, since they are constant. So we can cancel out the value k. So only for isotropic soil, this particular Laplace equation can be written as this: delta square h by delta x square plus delta square h by delta y square equal to 0. And this particular equation only valid for isotropic soil. Remember this. Since there is this particular k term is neglected. Why neglected? Because this kx and ky are eliminate each other, since they are same for isotropic soil. But in general, the general equation for Laplace equation is this one. Okay, so I prefer you to remember this thing: double differentiation of kh by delta x square plus double differentiation of kh by ky square delta y square is equal to 0. Okay, this, and from this you can derive, from the equation number 2 you can derive equation number 3 as well as equation number 4. Okay, so this is generally known as Laplace equation. Okay, so some very important of MCQ or MCQ may be generated from this derivation. So I advise you to go through thoroughly through this particular derivation. Okay, so this is all about today class. Next class we'll discuss about this particular velocity potential. Then we'll discuss about stream function, and finally we'll discuss about flow net. And flow net is very important, and it's used to study the seepage of water through them. Okay, okay, then so let's first close my sharing here. Okay, I'll share the notes in WhatsApp, so don't worry. And also you will get the particular video in YouTube also. Okay, okay, so I'll stop my recording, then I will take your attendance. Okay, wait.